All right, so this is one of the problems that we did during class, but if you need a refresher or if you were absent, this is a great way to do it. So this is for practice 4, conservation of energy. And what we have here is a 75 kilogram skier that's standing at the top of a 25-meter hill. What would his speed be at the bottom of the hill? Assume no energy is dissipated by friction. So what we'd like to do first is continue the 5-step problem that we were doing. And first we're going to draw a picture. So we want to know where the ground is. Okay, so we're going to draw that as our ground, and then our hill. And then on top of that hill, we have a skier. Okay. And there's a skier. All right. And let's just put in some details. So for example, the mass of the skier is 75 kilograms. And the hill that this skier is standing on is 25 meters high. And then we are going to write that he is not at the bottom. Excuse me. He's at the top of the hill. Okay. And so that's for the skier at position A. Now at position B, the skier is going to be at the bottom of the hill. So we're going to do the same thing. We're going to draw our ground so we know where it is. We're going to draw our hill. And now our skier is at the bottom of the hill. So he was here and then he ended there. All right, and so his mass, hopefully he didn't lose any mass along the way. So it's 75 kilograms, and we are looking for his speed. So this question is, what would his speed be? So that is our unknown. Okay, and so just to keep that in mind, oh, and we should also write that he is at the bottom of the hill. Okay. So I think we have more information given in position A, so we're going to go ahead and work with that. In position A, we are given the mass and the height. So we're going to assume we have the EG, okay, because of EG is equal to mg times h. He's not moving, so we know that there's 0 joules there. Nothing is stretched or compressed, so 0 joules here. And we're assuming no friction. Well, also, he hasn't moved yet. Okay, so our EG here is going to be the mass, which is 75 kilograms, times our little g, which we have known in class as 10 newtons per kilogram, and then our h, the height of 25 meters. Okay, and when we multiply this out, 75 times 10 times 25, so we have 750 times 25. I believe it's 18,750 joules. Maybe I should just double check that really quick. All right, fabulous. It was 18,750 joules. And since position A is only made up of EG, we know that the total is going to be EG plus EK plus EE plus ED. So 18,750 plus 0 plus 0 plus 0 is going to give us 18,750 joules. And that's what our total is going to be here also. So 18,750. And we know that there is EG, no EK, no EE, and no ED. So 100% of our 100% of this is going to be our elastic or our gravitational potential energy. All right, I'm just going to go ahead and color this in. This is a really good time to also bring your colors out. So if you have colored pencils, or I wouldn't suggest markers because it bleeds through into the other side. It's a good time to bring it to class. All right, and so the size of the pie represents the total energy. I'm going to go ahead and find a marker or make this a little bit thicker. Okay. So our full pie, the whole pie is going to be EG. So we color it in, and then we label it EG. All right, and so this is what position A would look like. Now we're going to go ahead and move on to position B. All right, in position B, he's at the bottom of the hill. So that means that he wouldn't necessarily have any, or he wouldn't necessarily have any gravitational, because at the bottom of the hill. So we're going to have 0 joules there. Nothing is stretched or compressed. So here you want to think about stretched or compressed. And since nothing is being stretched or compressed, we know that's 0 joules. And once again, we're assuming that there is no energy dissipated by friction, so this is also 0 joules. That means that we're left with EK, which is EK is equal to 1/2 mass times velocity squared. We also know that the total doesn't change because of the law of conservation of energy. So the law of, conservation, let me write that nicer. Conservation of energy. Okay, so that means that whatever was in position A, the total will become here too. So we have 18,750 joules. And since the only energy here is EK, we have 18,750 joules is equal to EK. Okay, and our mass is still the same, 75 kilograms. And when we isolated the problems from the previous practice, we know that, or I can show us how to, I'll work it out here too. Okay, we have, okay, we have, we're going to get rid of the 1/2 by multiplying by the reciprocal. So we have 2 EK is equal to mv squared. We're going to divide by the mass on both sides, but that cancels out. And so we have 2 EK over m is equal to v squared. And we want to know how fast he's going, so we only want one of these velocities, so we're going to find the square root of it. So essentially, the velocity is equal to the square root of 2 EK over m. And our velocity is going to be 2 times 18,750 joules over 75 kilograms. So here's the calculator. We have 2 times 18,750 joules. So we have 37,500. We're going to divide it by the mass of 75, which gives us 500. And we're going to square root that. So if you can see here in the corner, all the steps that I've been doing have been saved. And so you can see what buttons I'm pressing. We have 22.36. So we're going to go and just round to the nearest tenth. So V is equal to 22.4 meters per second. All right. And so we've done our calculations. We're going to go over here to the energy bar chart and pie graph. We have 18,750 here. And so we know that there is no EG, no EE, no ED, and that this whole thing is filled up by the EK. Okay, and same thing for our pie chart. We know that the whole pie, excuse my coloring. Okay, we know that the whole pie is going to be REK. All right, and so here's what our final problem might look like. There it is. Okay. All right, and so now we have finished the problem. We filled out our sketches. We acknowledge what position they're in. We also talked about the law of conservation of energy. So this total is going to be the same as position B's total. We also did our calculations for EG versus EK. And that is it.